So we're going to start off our new unit, Unit 4, by looking at the forces that are going to hold together molecules and compounds. When we have atoms that are connected to one another within a compound, within a molecule, we can describe how the electrons are being shared between them. Atoms are a nucleus surrounded by an electron cloud. Now when we form, let's say, the compound carbon monoxide, the carbon and the oxygen are sharing atoms so that they can form that cohesive compound. Now, this molecule, if we're sharing electrons between the two, can either evenly share these electrons, or there can be a pull to one side or the other. Think about what the charge is on the electron. The electron is negative, so if there's an uneven pull on the electrons, let's say if we pulled them too far to this side, if the oxygen was pulling harder, we might end up with a little bit of negative part over here and a little bit of positive charge over here. Now, electronegativity describes exactly how hard these atoms are pulling within their bond. So it would tell us, is oxygen pulling harder, is carbon pulling harder, or are they pulling roughly evenly? This is going to make a difference in the behavior of these molecules and compounds. So you'll be given a table of electronegativity, which we'll see a little bit later in the lecture. Now, if we have, and it's probably a bit hard to see, but this is a hydrogen attached to a Br, and this dotted line indicated that they're sharing their electrons. What we end up with is something called bond polarity. Bond polarity is when we get an uneven sharing of electrons between two atoms. These atoms are said to be bonded because they're connected to each other in a chemical compound or molecule. So HBr is bound together, and when we look at their electronegativity values, we see an imbalance. Recall, electronegativity is how hard an atom is going to pull electrons toward itself in a bond. So if H and Br are bonded, and this gray area surrounding the two atoms represents the electrons, then there's an uneven pull of the electrons towards the Br, which results in this funny symbol here. It's called a lowercase Greek delta and a minus. What that means is there's a little bit of negative charge over here. On the other side, we see that funny sign again, the lowercase Greek delta. We see a positive sign. That means things are a little positive on this side. Things are a little negative on this side. If you look at the direction the electrons are being pulled in, they're being pulled towards the Br. That means the negatively charged electrons are being pulled towards the negative side of the molecule. When you think poles, I want you to picture the Earth. The Earth has a North Pole, the Earth has a South Pole. Only in this case, instead of thinking magnets, we're thinking electrical charge. So one side is positive, one side is negative. That's where bond polarity comes in. If we had two atoms that shared perfectly, and they were connected by a bond, and we didn't see a skewing of that gray cloud to one side or the other, there would be no bond pole. All it would be is an even sharing of electrons between those two atoms. So, what we're going to end up doing is looking at the two atoms that are in a bond and looking up their electronegativity values and take the difference. So the math that is involved is subtraction. Depending on the difference that we get, whether it falls between 0 and 0.7, 0.7 and 1.8, or greater than 1.8, we can classify the degree of polarity between these bonds. Nonpolar would mean that we're looking at two atoms that are bound together where electrons aren't really pulled towards one side or the other, they're pulling roughly equally. That means we don't have a partially positive side and a partially negative side. If we have a polar bond, that means we're going to have a significant pull towards one side or the other. And finally, when we get to ionic, ionic is an extreme pull of electrons toward one atom in a bond, where one atom ends up taking the electrons and one atom ends up giving them away. So let's look at an example. We said in a previous example that HBr gave us a polar bond. Let's look at their values. H is 2.1 and Br is on the right hand side of the table at 2.8. The way we classify the bond is to take the difference, 2.8 minus 2.1, and always take the difference so that you end up getting a positive number. The difference here is 0.7. Let's see where that fell on our scale. If you look at the bottom of the slide here, we have a scale to help us categorize. Now, it falls exactly at 0.7, so it falls right between polar and nonpolar. We're going to lean towards this being a polar bond. Now, jumping back here for one moment, nonpolar and polar are different flavors of a bond type called covalent. Covalent bonds are where electrons are shared, and then it's further broken down into nonpolar, where electrons are shared evenly between the two atoms, and polar, where there's a pull towards one side or the other. When you guys are tested on this, you'll be given a difference in electronegativity that doesn't fall on one of the cutoffs, but that falls in between the cutoffs. It'll be very clear whether it's going to be nonpolar, polar, or ionic. Let's look at a difference here. Let's say I had the molecule O2. In the molecule O2, I've got an oxygen bound to another oxygen. What's the difference in electronegativity between two oxygen atoms? It would be 3.5 for one oxygen atom, 3.5 for the other, so the difference is 0. If we look that up on our chart, that's not just going to be nonpolar, it's going to be very nonpolar. It's all the way at 0. There's a special name for this. Pure. It is a pure covalent nonpolar bond, because in O2 we've got the same atom on both sides. It's not that there's close to no harder pull in either direction. There is no pull in either direction. The O2 is purely covalent, meaning it's purely sharing. Now let's do one example of an ionic. Now previously in the semester we've talked ionic compounds. We said you'd spot a metal in them or a polyatomic. So something like sodium chloride. If we look at the bond between an Na and a Cl, a sodium is 1.0 on the electronegativity scale. A Cl, found on the far right, is 2.9. So the difference between the two is 1.9. Now, on the previous slide, again, we can look this up. 1.8 is the cutoff between polar and ionic. We have a value that falls at 1.9. So we would call NaCl an ionic bond. So, given a bond, I'd like you to be able to look up the values on the electronegativity table for each atom in the bond and classify it based on the scale that you see at the bottom of the page here. Where nonpolar was where we had shared, polar was where we had electrons pulled towards one side more than the other, and ionic was the extreme pull where one atom gives away its electrons and the other atom accepts. Alright, so we can classify as covalent, we can classify as ionic, but now let's talk and refine our idea of different intermolecular forces. Inter means between molecules. Intermolecular, between molecules. We're looking at forces that exist between different molecules. So, The way that these work, we're going to have four different intermolecular forces we're going to look at. Three of these I would like you to be able to recognize. One of these, dipole-dipole forces, you won't have to recognize based on a formula, and we'll get into that more a little bit later. But what I do want you to have down is how they vary in strength. This is a huge thing to have down. Now, let's jump into our first. Ionic bonds. Ionic bonds deal with ionic compounds. Ionic compounds, we see a metal or a polyatomic ion that shows up in their formula. Now, ionic bonds have that extreme pull where one atom takes the electrons, one atom ends up giving away the electrons. So we end up with positively charged ions like the positively charged sodium, and we end up with negatively charged ions like the negatively charged chloride. And if you go back and ask yourself, what attract? Two positives, two negatives, a negative and a positive, it's going to be opposites. So a green negative ion, the larger ion, is going to attract to the smaller positive ion. So if you look at what they're surrounded by, this little positive ion in the purple here is surrounded by larger negative ions on all sides. This is called a crystal lattice. It's a regularly repeating structure, which makes the structure cohesive. So we'll label this crystal lattice. And this is an incredibly strong interaction. It is the strongest of the interactions. It's the only one that's going to form this crystal lattice structure. And it's the only one that we'll see for ionic formulas. Alright, hydrogen bonds are an incredibly strong intermolecular force themselves, but they are weaker than the ionic bonding. Hydrogen bonds you're going to recognize because you'll see an H directly bound, meaning there's nothing in between them, to an N, O, or F. So let's take water for example, H2O. O is going to be linked directly to two hydrogens. This is what I mean by linked directly. There's no atom in between here, it's just O directly connected to H. Now, if we looked at the electronegativity values for oxygen and for hydrogen, let's do that. Let's flip back to our electronegativity table. Oxygen is 3.5 and hydrogen is 2.1. So, if O is 3.5 and H is 2.1, their difference is 1.4, which classifies it as covalent, so there are electrons being shared, and it also classifies it as polar. So we have a pull towards one side or the other, and the electrons are going to be pulled towards the more electronegative element. That's a key statement. The electrons will be pulled towards the more electronegative element, so oxygen. So if we draw in little arrows on these molecules, I'm going to pull electrons toward the oxygen in each one of these molecules that are shown in the lower right. So in the direction of the arrows, I have a little negative area. That means that where the electrons came from over on the hydrogen side, I've got a little bit of positive. And if you look at where things line up, this is what a hydrogen bond is composed of. It's negatives attracting to positives. We've got opposite charges that are attracting. And that's brought about by the polar OH bond. Now, every one of these forces is going to have something in common, and that's the sense that opposites attract and negative charges attract to positive charges. The way you're going to distinguish hydrogen bonds is that hydrogen bonds always have hydrogen, but more importantly, that hydrogen is directly connected to an N, O, or F atom. Alright, on to the dipole-dipole force. Now, similar idea, we're going to have a partial negative and a partial positive charge, and that's brought about by electronegativity and a pull of electrons towards one side or over the other. But because we have to arrange these atoms in three-dimensional space, sometimes these can be a little tricky. So let's look at carbon monoxide. This is something we looked at a few moments ago. If we have 2.5 for our electronegativity value for carbon, and we've got 3.5 for oxygen, that relates to a difference of 1.0 in electronegativity. Oxygen is the more electronegative atom, so we're going to see a pull towards the oxygen. Now if we change gears and we look at CO2, between each one of these, we're going to see a difference of 1.0, just like we saw in carbon monoxide. If we look at their differences in electronegativity. Oh, I'm sorry, I switched those. This should be 2.5. And the outer oxygens. Oxygens are the smaller spheres shown in red, should be 3.5. Now, difference of 1.0 in each one of their electronegativities. So I'm going to be pulling outward toward the oxygen in either case. Now, these happen to be at 180 degrees. So they are flat out from one another. If we were to draw it over here, I would have an oxygen, a carbon, an oxygen. And I have an equal pull in either direction. So the bond dipoles, we would say cancel. So I don't really have a negative side over here or a negative side over here, because they're pulling equally and oppositely in direction. So a dipole-dipole force requires that you don't have this cancellation of poles. You have to pull in one overall direction. A molecule has to have, if we draw just a generic molecule, a molecule has to have a negative side where the electrons are being pulled to and a positive side where they're being pulled from. That way molecules can attract and repel one another. CO has that because there's no pull to counter out the carbon-oxygen pull. CO2 doesn't have that because it ends up pulling in equal and opposite directions. Now, I'm not expecting you guys to recognize these on an exam or on a quiz because we haven't covered how to determine three-dimensional shape. That's a topic not covered until 151. So if a molecule has dipole-dipole forces, I will be notifying you. So let's take another look at this. Let's say we have something like Br F5. My Br is going to go at the center. I'm going to show you guys the overall shape of the BrF5 molecule. We end up having where these dashed lines are going back into the screen and these bolded lines are coming out at you. We're going to start out with this shape that ends up being pretty much like a flat sheet where one F goes here, one F goes here, we have an F here, we have an F here. Then we're also going to have one F that shoots up above. So we'll have that F here. Now, let's go back and look at our electronegativity values for Br and for F. For Br, we've got a value of 2.8, and for F, we've got a value of 4. So 4.1. So that gives us an overall difference of 1.3 between the Br and the F. And that's the same for each one of these bonds. So each one of these bonds is considered polar. It's also considered covalent because we've got a difference of 1.3. And we're going to see these pulling towards the more electronegative atom. So the F, all the electrons are pulled out towards the F's. Well, now we have to look. There's going to be some cancels here. These are on opposite sides, so they're pulling equally and oppositely. These are on opposite sides, so they're pulling equally and oppositely. This isn't canceled though. So what we end up with are electrons being pulled up, which gives us a partial negative up on this side and a little bit of positive from where they're being pulled from. So this would be considered a polar molecule. And if we had, just generalizing again, BRF5 molecules, I'm just generalizing as this M with a circle on it, there is an overall pull of electrons towards one side or the other. So if a BRF5 happened upon another molecule, its positive side would attract to the first molecule's negative side, and so on. If we had another molecule, its positive side would attract to the second molecule's negative side, and we would keep getting interactions like this. Now, the difference between dipole-dipole forces and dispersion forces is that dipole-dipole forces are going to be there permanently. They're called permanent dipoles. Dipole-dipole and hydrogen bonding and ionic forces are always going to have their poles in place. They have permanent dipoles. But when we get to dispersion forces are called instantaneous dipoles, or they're called come and go dipoles. They're there one moment, they're gone the next. Think of an atom. At the very center of the atom we have a nucleus. On the outside of that nucleus we have an electron cloud. Now, if it's perfectly balanced, then that atom has a roughly evenly distributed electron cloud. But if for a moment it shifts to the right, then I would have more negative charge on this side because the electrons are shifting toward that side, and a little bit of positive charge on this side. With dispersion forces, we depend on the electron cloud having a little bit of play, being a little bit squishy in the sense that it can shift towards one side or the other. Now, taking this example on the center of the page here, we have two atoms that are bound together in a molecule, and they're sitting right next to another molecule. Now let's say that in step 2, the electrons are pulled towards the left-hand side. That's why the cloud gets bigger on the left-hand side. If electrons are pulled towards the left-hand side, I've got a little bit of negative charge over here, and I'll have a little bit of positive over here. Now, this molecule hasn't noticed this yet, but when it does, it's going to shift. This shift that we saw in this molecule is called an instantaneous shift because it's not going to be permanent, it's just temporary. But when this molecule on the right notices that the molecule on the left has shifted, because we have a little bit of negative here and a little bit of positive here, the electrons in the second molecule are going to be drawn to the left. They're going to be drawn towards that other molecule, resulting in a little bit of negative here and a little bit of positive here. Now, question to ask yourself is, are molecules stationary? Do they just sit in one place? And the answer is no. Depending on the state, they'll be vibrating, they'll be translating, they'll be moving all around. So these two molecules aren't always going to be next to each other. So, gone one moment, there the next. One molecule having a shift in its electrons towards one side or the other can create a temporary pole. You can have a temporary negative side and a temporary positive side. If it comes across another molecule, it can induce that dipole, called an induced dipole. It can make another molecule have a temporary dipole, but when they separate again, that dipole will be gone. So dispersion forces, because they have dipoles that come and go that aren't there permanently, are going to be very, very weak forces. If you look back in your notes at strong to weak for intermolecular forces, dispersion forces are at the very bottom of the barrel. They're the very weakest force that we have, and the reason is because they're not there permanently. It's because they come and go. Now, how to ID these? Well, in a nonpolar molecule, which is a molecule which either doesn't have polar bonds or they all cancel out. But for the most part, when you identify a dispersion force molecule, it's going to have nonpolar bonds. So something like O2. If we look at the difference in electronegativity between those two O's, doesn't matter what the value is, we would be subtracting the same value from the same value. They have a difference of 0. So it is pure covalent, or purely sharing. So because there's no pull towards one side or the other, that makes this nonpolar. There's no positive side, there's no negative side. So we're not going to end up having anything but dispersion forces. If a molecule is nonpolar, which hydrocarbons or molecules that have all nonpolar bonds, which you'll have an electronegativity table handy, we can identify as dispersion forces, being their primary intermolecular force. Alright, thanks for being here for Unit 4 Lecture 1, and make sure to catch Unit 4 Lecture 2.